Our next speaker, Dr. Nick Nystrom, is the Director of Strategic Applications at the Pittsburgh Supercomputing Center. Nick leads a team focusing on developing hardware as well as software architectures that really enable research in data-intensive and computational science. Nick has a bachelor's degree in chemistry, math, and physics, as well as a PhD in quantum chemistry from the University of Pittsburgh. So clearly he knows what he's talking about. Some of his other research interests presently include causal modeling, in which he's collaborating with one of our previous speakers, Dr. Greg Cooper, and also focusing on graph analytics and programming languages for exploiting concurrency and heterogeneity. So I'm sure Nick's talk is going to be very interesting. I'm excited to hear it. So at this point, I'll turn it over to Dr. Nick Nystrom.
Okay, thanks, Ryan. So as Ryan said, I'm going to be talking about a new project at the Pittsburgh Supercomputing Center. It's called the Data Exacell. We've heard all day today about ways people are using big data. We haven't heard a whole lot about the infrastructure that actually makes that possible. And I'm going to be talking about some of that today, along with some applications. First, the PSC, I'll say a few more words about that in a minute. But we've been around for 28 years. And in my view, we've always been doing big data. What big data means is what has been changing. So historically, we were focused on the problems you would associate with supercomputing. And so those were things on the left with large instruments like telescopes, gene sequencers, or with the outputs of very large-scale simulations, such as climate modeling. What we're seeing more recently, both in the research landscape and the private sector, is a shift to looking at all sorts of other data, everything from social networks, very large-scale video data, video surveillance, for instance, lots of integration of legacy data. So paper stacks of documents, they have to be digitized, scanned, OCR'd, and otherwise parsed. I like this picture. This is from the Library of Congress. And all of the little yellow tabs on these shelves are tags on these documents that say the paper is fragile, be careful when handling. And so these are documents that can't even be accessed indiscriminately, like you think of old documents being accessible. These will wear out. But there are also other forms of data. On the bottom is just a tray of butterflies. The Carnegie Museum of Natural History at any time has about 10% of its samples out on loan to researchers worldwide. Obviously, when a tray is out on loan, it can't be used by anyone else. And these also have a finite lifetime. So it'd be nice to digitize all of that to make it available. And the bottom just represents sensor data, which is another source of very large data. In this case, it just look at sea temperature, and the data comes from a sensor you might not expect. It's from temperature sensors are tagged on hooded seals that just tend to swim and go places that people don't normally go. That's a nice source of data. And so what we're finding is very different data sources. It's very unstructured. It has a very high variety. We heard a lot this morning about the V's, and a previous speaker on the morning panel was mainly focusing on velocity and variety. So this is tremendous variety, bringing together different formats, doing cross-analyses between them, and also dealing with things that scientifically were not previously high on the radar. And with that brings new areas of emphasis. Whereas we used to focus a lot more on very structured things, doing statistics, numerical optimization, scientific visualization, things like that. Now we've moved into very unstructured data. Machine learning is a very important part of this. We have a lot of collaborations going on with people in Carnegie Mellon's School of Computer Science, for instance. And then everything goes with that: natural language processing, analyzing video data, graph analytics, the things that the previous speaker, if anyone was in this session, was alluding to that civic science is doing, and looking more toward information visualization. A few words about PSC for those who don't know us. We're a joint project of the Carnegie Mellon University and the University of Pittsburgh. We've been around since 1986, co-founded by a pair of physicists, Ralph Roskis, who's in the audience here, and Michael Levine from Pitt and Carnegie Mellon, respectively. And we've provided national leadership. We're a national supercomputing center, and we provide leadership in providing high-performance data-intensive computing, software design, scalable software and algorithms, And we really serve the academia, the research community, but also look to promote industrial competitiveness and, of course, the region. And we're supported by a variety of agencies, including NSF, the NIH, and others. The data exacell I'm focusing on today is a National Science Foundation funded project that is 1 year into its 4-year cycle. And it is a pilot project really designed to integrate high-performance analytics with storage. And so this is different than some of the things that people think about just building a Hadoop cluster or other things. It's really looking at having very large-scale, innovative, high-bandwidth, low-latency storage, and coupling that to state-of-the-art computing resources. And we've also added capability to support modern database technologies because that's greatly needed. The data exacell, or DXC as we call it, is highly application driven and motivated. I'll run down a list of applications we have on this. Just to give you a feel for the breadth of research that's covering. It extends things we've been doing at PSC in important ways. And the things it extends, and I'll have one slide on each, are the data supercell, which is really innovative disk-based storage. Blacklight, which is, there's the right button, which is the world's largest shared memory computer. And shared memory is important for this because in many cases, the application bases are written in things like Java. And people want to be able to scale things they've done from their laptops on up to a machine that has 16 terabytes of memory. Sherlock is a unique machine that is purpose-built for graph analytics. And that would be like the very large sparse networks we saw in the previous speaker's talk, or 2 speakers ago with civic science. And then adding databases, as I mentioned. Looking at the overall architecture, we have these resources just conceptualized in the top row. So the storage, large shared memory, graph analytics, and database and web services for distributed systems. And those are coupled over high-speed networks. We have a 100 gigabit link out of PSC to the world. And that then connect to everything, government, private sector, obviously campuses, researchers. XSEED is the National Science Foundation's advanced cyber infrastructure for doing advanced computing across the country. There are other centers in it. And then state-of-the-art instruments. This is the single dish telescope down Green Bank in West Virginia. And so as I said, it's funded by NSF. It's funded by a project called the Data Infrastructure Building Blocks. And so its purpose is really to develop, test, implement hardware and software building blocks that can then be used to inform other future architectures and acquisitions in the advanced cyber infrastructure landscape. And that's across the country and at PSC. And for example, things that we expect to come of this, or we've been working on an innovative file system called /2 and improvements to that. Software for really coupling applications of all kinds between these very large analytical engines and very large storage using various database and other technologies. This ties to the work that Greg Cooper described at the 1:30 session that was in this room on the NIH Big Data to Knowledge project. Doing distributed workflows and so on. So there'll be a large number of these. They're already starting to emerge. And then the opportunities that come from this, and this cuts across private sector and academia, are one is just finding subtle patterns and relationships in big data, both causation-based, as Greg described a few hours ago, and also some of the other things we've seen today. Doing real-time analytics to inform decision-making. We have been talking to people in the private sector about large data sets they have and ways that we may be able to help them. Their data sets right now are, everyone asks today, how big is your data? The data exacell, I should say, we've designed it to have about 5 petabytes of storage to start with. It really is just a pilot project. In something else we hope to be able to announce very shortly, so watch the PSC website or other media. We'll have somewhat more and more of a production scale, but this is a pilot. And the data sets we're talking about then for working with people, at least in the private sector, they seem to be of interest around 100 terabytes. Really doing analyses across domains is a key here. People have a lot of data. They tend to be in different formats. They have not looked at them together yet, and they'd like to do more of that. And then folding in legacy data. So we've talked with a number of groups. We actually did a pilot with the US Navy. And a lot of them have legacy data. It could be on paper records, it could be digitized, but it's in old formats, and they'd like to make sense of this. A lot of it's still important because there are a lot of systems out there that are still running. As we heard in the morning panel, the gentleman from Rolls-Royce described systems they have a 20 or 30 year lifespan. With the Navy project we were looking into, these are submarines that have a 50 or 60 year lifespan. So moving to the technologies underlie this, /2 is a distributed file system that was developed at PSC. It's available at this website if you want to learn more about it or download it. It really is an encapsulating file system. So it brings together any other POSIX compliant file systems. It could be NFS, Lustre, GPFS, what have you, and provides a number of capabilities designed to be wide area network friendly. It gives multi-residency at the chunk level. So if you have files at multiple sites and if you do updates, not only do the files migrate across as you choose, but you can update a block of a file, and then only that block will be migrated. So there are a lot of things in here. They're designed for both wide area functionality, collaborations between groups or whoever working at a distance, and dealing with big data. So there's inline checksum verification. You want to be sure that the data is moving across correctly. And a number of other features here you can read. The extensions that we're doing for the data exacell then really focus on doing the distributed computing aspect. We have /2 instances. It's freely downloadable. I haven't looked at how many people have done that, but we have instances set up, and for this purpose, there's one over the Pitt Department of Biomedical Informatics, so the group that Greg Cooper represents, and there's also one over the Pitt School of Information Science, and these are research collaborations we're doing at a distance. And they're allowing distributed web-based workflows, so data can be at their research institutions for doing certain analysis, and then for doing other larger scale things using the unique resources at PSC. And then other improvements for ease of use and performance. This is really an old technology. This is the data supercell. It's been in production for over 2 years, probably going on to 3. And the whole point here is that it gives us very high bandwidth, low latency storage that is fully scalable in performance and very cost effective. And so for a research setting, it's ideal. For other settings, it's also ideal. And there's space available on it. It has all the normal things you'd expect. So very high reliability. We've designed this to be easily scalable to the petascale level. And so we're paying attention to things like 3-bit errors on disks that do happen at that stage. And you want to be able to detect and avoid those so you don't have silent data corruption. And that's what we're extending for data exacell as the underlying storage layer. Now we're moving to much higher bandwidth and better performance. Blacklight is our shared memory resource. And as I said, it's 16 terabytes of cache coherent shared memory. That's a hardware limitation based on the processor. So we have 2 of them because we can only go up to 16 terabytes each. And we find out that that's actually a nice size. It's sufficient for what we want to do. This is very important, we find, for machine learning because these people have code bases of millions of lines of Java code, just packages on packages, and they want to be able to run that without porting it. And so we can provide a high-performance computing solution for existing code bases. And then it has all sorts of hardware optimizations for making it run fast, and I won't go into detail on that. But these are things you just can't do on a cluster. The other resource that's in the data exacell now for doing computing is Sherlock. We named it that because its purpose in life is to find subtle patterns in big data. And as the president of this company used to say, it's not for finding the needle in a haystack, it's for finding the needle in a needle stack where the data all looks kind of alike. And you want to find the different little patterns in it. And so this has both custom processors and custom internal network to allow it to have, first of all, very large shared memory space. You need that because graphs are not partitionable. You can't separate them across a Hadoop cluster effectively. And to let things run very, very fast. On top of this, it has a very easy to use software layer based on W3C standards, a data format called RDF that you may know about, and a language called Sparkle, which is kind of like SQL for graphs. And so it's easy to use. I will spend a few minutes talking about the applications that we have on the data exacell, because it really shows you the variety of things we're applying it to. And this pilot was always meant to be very application driven. We wanted to look at applications that had different requirements on what they need to do for big data analytics, and then make sure we developed a system that would serve them all. And so the initial 5 that we had in the project were this set on this page. So there's the Pittsburgh Genome Resource Repository, and it ties to things that were in the previous talk. There's a data set called the Cancer Genome Atlas that right now is about 1 petabyte. And that is now hosted over at Pitt, and it's being exchanged between Pitt and our place through /2. And this is looking at changes in gene pathways that cause tumors. So it contains data on about 40, I believe, different types of tumors, several hundred patients each, and the full genome sequence data. So you're looking for which genes are implicated in which cancers and how they relate to each other. The second project, Semantic Understanding of Large Multimedia Data Sets. This is looking at feature detection in large collections of video and doing it at a very high level. So for those that were at Jerome's lunch talk on Watson, it kind of reminds you of that. So they get annually a large collection of video. This is a competition. So they get thousands of hours of video. They do machine language or machine learning on it. They do language translation from all of the text that's in the video, all the speech down to text. They build a semantic model. They do semantic indexing. At the end of the competition, then they are given challenge phrases like, show me all the video clips that show somebody fixing an appliance or someone batting in a home run. So these are very high-level concepts. They're not things that computers just naturally understand if you did, say, Google search on that, Google Images. And then they find the video clips that pertain to all these things, and they actually won all of the categories in this year's competition, so it's a project that's going very well, and it heavily uses blacklight and obviously storage. The project here from the National Radio Astronomy Observatory is really looking at bringing together different data sets. So these are astronomers. At NRAO, obviously, they're radio astronomy, but they're interested in looking at astrochemistry and the chemistry of exoplanets, so planets in other solar systems. To do that, they want to bring together data from all wavelengths, ranging from infrared up through X-ray. These exist in different formats. They've been from different communities. The data have different formats. They have different representations. They have different time scales. They represent different areas of the sky. And so bringing those together is where it's one area where we want to have these databases brought to bear as a challenge, bringing together these different kinds of data sets. I want to jump down to the bottom one, this data integration fusion for world history. Thank you. And so that is an example of one where the whole purpose is bringing together different data sets from world history, economics, sociology, and so on. So I think I just want to jump forward. We have a number of other projects in everything. This is the center that Greg described, optimization, analysis of financial markets. This is a project that actually influenced the New York Stock Exchange. In previous research, the group did it from University of Illinois, and so on. The current status is that the hardware is here. We're implementing more as we go. We're adding new pilot applications. That's just limited by our own ability to help them come on board. Contact me if you might have any ideas. And overall, it's building blocks that are going to be put into use both nationally and in other systems. You'll see a PSC very soon. So I'd be happy to take any questions.
The /2 distribution file system, what is the block size default?
The block size, well, it's a /2 federates underlying file systems. The question was, what is the underlying block size for the /2 file system? Because it brings together underlying file systems that can be whatever you have, the block size is the block size of your file system.
It's not how different it is for Hadoop distribution.
/2, I don't believe anyone has tried to use it with HDFS. I'm not sure it would make a lot of sense.
Yeah, HDFS do replication by default, do 3 times. And this also do the replication. But is there any default?
So the question has to do with replication. So we look at it differently. HDFS does default 3x replication because it assumes you're building your system on underlying low reliability components. We tend to assume that we build parallel file systems of high reliability components. So within a file system, we will do high-level RAID. We're doing 8+3 on ZFS. So we have very high, very high data reliability. In our experience, rebuild times are not an issue. We would do replication primarily if people want to use the data at different sites, if they want local copies. So we would do replication to have data locality, not for resilience. Any other questions? Okay, thank you.